Picking back up where we left off, we're going to talk about expressing concentration mathematically and numerically. So the first way that we express the concentration is using something called molarity. The formula for molarity is the number of moles of your solute divided by the liters of the entire solution. So this is your solute and your solvent together. And remember from the previous discussion, we talked about how if you have like 2 milliliters of solute and then 2 milliliters of solvent, or 2 and 3, it may not equal 5, or it may not equal what you think it would. So you really have to measure your liters of solution after you mix the two together, because it may not be exactly additive. If we're looking at a word problem, it will usually tell us the volume of the solution, or it will tell us that the volumes are additive, meaning we can just add the solute and solvent together. And then on the top, you have moles of your solute. Molarity is symbolized by a capital M, and it can change with temperature because volume changes with temperature. The other way that we can express the concentration is in something called a mole fraction. And we usually use this for gas mixtures, mainly. So a mole fraction is symbolized by the letter X, and then you'll have a subscript that tells you what you're telling the mole fraction of. So you can have the mole fraction of iron, and that's going to tell you how many moles of iron are in the entire solution, okay, in a fractional form. So X is always the symbol, but then this A, this A right here just means the element or compound that you're talking about. So then whatever you're finding the mole fraction of, the moles of that thing go on the top, and then the moles of the entire solution go on the bottom. So everything, moles of everything on the bottom, moles of the thing that you're looking for on the top. So if I wanted to find the mole fraction of oxygen in the air, I would put the number of moles of oxygen in my sample on the top and the moles of everything, including the oxygen, on the bottom. Mole fractions do not change with temperature, and that's advantageous with a gas because gases, their volume can change so much with even a little change in temperature. So we would rather use mole fraction for gases, and we'll use molarity most of the time when we're talking about liquid solutions. All right, so here's our first example. We have a 3.75 gram sample of sodium chloride, and we're dissolving it in water, and then the total volume of the solution is 768 milliliters. What is the molarity? All right, let's take a step back for just a second and talk about what type of solution this is. So we have sodium chloride, which is what type of compound? Ionic, and we're dissolving it in water, which is polar. So we're creating a solid in a liquid solution, and we're going to have an ion dipole interaction. All right, let's move on to looking at the math here. So for molarity, we have moles over liters. So the first thing we've got to do is change the grams of sodium chloride, which is our solute, into moles. So remember to do that, we multiply by 1 mole over the molar mass from the periodic table. So there we have moles of sodium chloride. Right? Then to find the molarity, we divide those moles by the liters of the solution, which was given in the problem in milliliters. So we move the decimal 3 places to the left to change that to liters. You see the value on the bottom here. It's now in liters. And then you simply divide to find the molarity. This is written in scientific notation, but you could easily write it as 0.00, just 1 0. 0.0836. Remember, your unit for molarity is a capital M, or you could write moles per liter. All right, the next question says how many milliliters of this molarity, sodium hydroxide, are needed to deliver 1.7 moles of sodium hydroxide. All right, so let's think about the question. We have a solution of sodium hydroxide that's already made, so it's already in the bottle, inside the water, in the liquid form, and we want to get 1.7 moles of sodium hydroxide from this solution. So we have our molarity and we have our moles. We're looking for our liters, or the milliliters. So whenever you see this capital M, whenever you see this, always think of the equation molarity equals moles of solute over liters of solution. So here's our equation. We have this piece, we have the moles piece, we're looking for this missing liters. All right, so let's work it from there. So we have 0.245 molarity equals 1.75 moles over an unknown amount of liters. So we're looking for L. Now first we've got to get L out of the denominator. So we're going to cross multiply. So we're going to have 245 molarity times liters equals 1.75 moles. Okay, now this is a two-step problem since liters was on the denominator. Now we can divide to solve for our liters. Dividing by 0.245 on both sides to solve for liters. Alright, now remember that molarity is moles per liter, so the moles will cancel and that'll just leave me with liters for my answer. So I'm going to say that my liters equal whatever 1.75 divided by 0.245 is. Alright, so I'll let you do that math. I don't have my calculator with me. Once you find that, that is your liters, but they're asking me for milliliters. And so I will have to multiply by 1,000 or move my decimal 3 places to the left in order to solve. Now what I want you to show you here is they're going to use dimensional analysis to solve this problem. So they're starting with their moles and then they take their molarity and they say, okay, we know that molarity means moles over liters. So moles over liters, we can flip that over so that our moles will cancel and then we'll have liters, which is what we're looking for, right? This is the exact same thing that we just did. 1.75 divided by 0.245. Just a different setup. So it depends on which way you want to think about it. You can think about it in the equation, molarity equals moles over liters, or you can think of it as dimensional analysis. Then in their second step, they're going to change it to milliliters. So the answer, either way you solve, should be 7,140 milliliters. That's how much you're going to need of this solution if you want 1.75 moles of sodium hydroxide. All right, next question. You are trying to make a specific solution. So you need to prepare 100 milliliters of a 1 molarity solution. But you only have a 1.25 molarity solution. You have some water that you could use as well, and then you have 100 milliliter graduated cylinder. How would you do this? How are we going to make a solution from a solution? Right, this is a process called dilution. Okay, dilution is when you have a solution of higher concentration and you're trying to change it into a solution with a lower concentration. So in dilution, you're taking a solution of higher concentration, higher molarity, and adding water or solvent of some sort to change the solution to a lower concentration or lower molarity. Okay, this is called diluting the solution. There's a special equation that we use when we're diluting a solution, and that is M1 V1 equals M2 V2. And what does that mean? Okay, that means that your first molarity, that's your higher concentration, times the volume of that solution is going to be equal to your second molarity, that's your diluted solution, your lower concentration, times the volume of that solution. All right, so let's look at the information we're given and see how we could solve that. See if I can make this text box bigger. Sorry, that disappeared. Rewind, okay, if you need that information again. So we've got M1 V1 equals M2 V2. So first off, here is the information about there's the box back if you need it. Let me go to my drawing. This is the information that we have about the lower concentration, the diluted solution. That's going to be my M2 and my V2. And then I know that I have this concentration of my more concentrated solution. That's going to be my M1. I'm trying to figure out how much of that M1 I need in order to make this less concentrated solution. So we're going to take this 1.25, that's our M1, 1.25, sorry for the typing, that's molarity, times, we don't know how much of that we need. So we've got our unknown V1, and that's usually the case. All right, and then for our second molarity, we want to create a 1 molar solution, and we want to create 100 milliliters of it. So that's going to be our second volume. So the question is, how much of that do we need to create the second solution? So we'll multiply and then divide by 1.25. Okay, and you can do that math. Again, I don't have my calculator. But you'll be finding out what your volume is that you need, and that's the volume of the 1.25. Now, ultimately, you want to make a 100 milliliter solution. So how do you take this V1 that you get and make a 100 milliliter solution out of it? You add water. And the water is what makes your concentration go down. So the question it's really asking is, how much of the solution do you need? And then you're going to add water to it until you get to 100 milliliters. Okay, so let's look at how they work this out. They're not going to use the M1V1 equals M2V2 equation. Okay, they're taking a little bit different path. So you can look at their steps here. But this equation is a bit of a shortcut that I like. So taking a dilution, we can use this equation. We need 80 milliliters, which is hopefully what you got when you did the math earlier. 80 milliliters of that 1.25 solution. So then what do we do? Because the question is, how would you do this? Not just the math. So you're going to take the 80 milliliters of your more concentrated solution and put it into the graduated cylinder. And then you'll add water until you get 100 milliliters. So how much water are you going to be adding? You'll be adding about 20 milliliters of water. So that 100 milliliters that they asked for would be your total at the end. Okay. Apparently I can't get rid of this box now. Alright, our next example is a mole fraction example. They want us to find the mole fraction of KOH and the mole fraction of water in a solution that is prepared by mixing, and then it tells us we have 1.5 moles of KOH into 1 kilogram of water. So in order to find the mole fraction, you have to know the moles of the thing that you're looking for as well as the total moles. So first they ask us for the mole fraction of KOH. Well, in order to find that, we've got to know the moles of KOH and the moles of water. Well, we already know the moles of KOH. That was given to us here. But we have no idea what the moles of water are. We only know that it's 1 kilogram. So our first goal is to find the moles of water. So here we go. We've got 1 kilogram of water, so we're going to change that to grams. And then we can change grams into moles using the molar mass, of course. So there's the setup for that. And then from the math, we find that that's 56 moles of water. So we have 56 moles of water and 1.5 moles of KOH. And those are the only two things in the solution. So now we're ready to find our mole fractions. So to find the mole fraction of KOH, we would write that as X. That's our symbol for mole fraction. And then KOH is your subscript. It tells you what you're finding the mole fraction of. Whatever you're finding the mole fraction of, moles of that thing go on the top, and then your total moles of everything in your solution go on the bottom. So here we have 1.5 moles of KOH, and then we found out that we have 56 moles of water, and we'll add that to our 1.5 moles of KOH. So make sure you put this in parentheses on the bottom, and then we'll divide. And we find out that it's 0.026 mole fraction KOH. Mole fraction has no units. So molarity is moles over liters, but mole fraction, you're dividing moles by moles, so they cancel. No units. Sorry about this thing. I don't know how to get rid of this. Move it up here. All right, so mole fractions always equal 1. Okay, mole fractions always equal 1. So if you know that the KOH mole fraction is 0.026, you can subtract that from 1 to find the mole fraction of water. However, I would rather just calculate the mole fraction of water to be sure. So the mole fraction of water is going to be moles of water, which is 56 moles, over your total moles, which was 57.5 from the water and the KOH. And then, of course, your moles cancel. If you divide those two, you should get something really close to this 0.974. The reason that your mole fractions add up to 1 is because 1 is the whole, if we're talking about fractions. So if you have a fraction of your solution is KOH and a fraction of your solution is water, together they make up the whole solution. So they should add up to 1. All right, we'll pick up here with these last few things on the next video.